So let's welcome Professor Wheesoh Lee again, and he will continue his lecture on physics and mathematics of Calabi-Yau manifold.
Okay, thank you. So yesterday I set up the various concepts in Calabi-Yau manifold, and I started talking about the supersymmetric sigma module whose target space is Calabi-Yau. So I ended up with a description of L equal to superconformal algebra. In 2 dimensions, and it's an infinite dimensional symmetry, so that helps us understand the system enormously. I hope you can read this. Do you want me to make this bigger a little bit?
Maybe a little bigger.
Okay.
No?
So one of the important thing about conformal field theory in general is that there is a state operator correspondence. For each normalizable state, there is an operator and local operator and vice versa. So for state, you have an operator. So if we are considering 2 dimensions, so we have one complex coordinate, and so this is a very useful notation. So now we have L equal to superconformal algebra. So that means that Hilbert space, the total Hilbert space, is decomposed into representations of superconformal algebra. One of the generator of superconformal algebra is Hamiltonian, whose spectrum should be bounded below in any unitary quantum theory. So that means that the representations that appear here should be highest weight representations. So that means that there is a highest weight state. So for representation, of this algebra, we have a highest weight state. For which I use the same notation phi, which get annihilated by annihilation operator in the algebra, which I used this notation to denote generator of this algebra yesterday, where if n is greater than 1 and r is greater than 1/2. I'm assuming that r takes value in half integer, half odd number. Then this is annihilated. So this is the highest weight representation. So any unitary representation of this algebra can start from this highest weight state and apply other generator of n equal to superconformal algebra to make representations. And so basically this summation then will be sum over highest weight state, highest weight representations. But there is a particular representation, highest weight representation called BPS representation, for which in addition to this, you postulate that it is annihilated by G minus 1/2 plus or G minus 1/2 minus of phi. You cannot impose both, so you can impose either highest weight state is in addition annihilated by this or this. Please note that here, the grading here is minus 1/2, so it's a negative number. So it's not included in here. So this is an additional condition. Okay, so if a highest weight state satisfies this additional condition, then it's called BPS state. Okay, so now suppose you have such BPS state, and so one of the features of this BPS state is that in general, if you have a highest weight state, you can choose the highest weight state to be eigenstate of L0. The Virasoro generator on J0, the charge. But if you have BPS, then this highest weight H, the conformal dimension, is equal to 1/2 of absolute value of the U1 charge. So this is sort of one of the conditions. In general, if you have non-BPS, H is greater than 1/2. So as you decreases h and it hits at h for 1/2, you can decompose the representation into BPS representation. Okay. So BPS representation, BPS plays various important roles. One of the roles is the following. So suppose you have 5, which is a BPS, and I said that there is a choice of whether it's annihilated by G plus or G minus. So that's for the left moving part, but you can also have right moving part. So that means that there are actually 4 possible choice of BPS state, because it can be annihilated by G minus 1/2 of plus or minus, and it can be annihilated by G bar, the right mover of G plus minus 1/2. So you have a 2 choice here, and you have 2 choice here. So in total, you have 4 types of BPS state. Okay, so we call this tentatively, we call this for convenience, like if it is annihilated by G minus 1/2 plus and G bar minus 1/2, we call that as CC primary. And then if it is annihilated to G minus 1/2 minus G bar plus minus 1/2, then we call that as AC primary. And then there are other types. So G plus and G bar plus and G plus. Oh, sorry. G minus and G minus and G bar minus. If this is annihilated by that, minus 1/2, then we call that as AA. And plus minus 1/2 and minus. And then this is called CA. I hope the notation is clear. This C stands for chiral. And A stands for anti-chiral. Okay? And so you have these 4 types of BPS states, BPS operator in this kind of series. And these can be used for a variety of useful calculation. And one important thing is the following. So I said that we are considering 2-dimensional sigma model, 2-dimensional n equal to CFT, which is described by map from 2-dimensional surface into some Calabi-Yau manifold. And then with some fermionic degrees of freedom. In general, the Calabi-Yau manifold comes with parameters called moduli. And there are 2 types of moduli for Calabi-Yau manifold. So one is called scalar moduli, and the other is called complex structure moduli. Scalar moduli includes the size of the Calabi-Yau manifold. If you have a Calabi-Yau manifold, you can actually just increase the size of the Calabi-Yau by multiplying constant to the metric, for example. And that is a moduli of the Calabi-Yau manifold. Okay. Complex structure is that where Calabi-Yau manifold it comes with scalar, it's a scalar manifold, so it has a complex structure. You can deform complex structure and you still have Calabi-Yau manifold. And in fact, Yau's theorem says that if you fix a scalar class and complex structure, then there is a unique Calabi-Yau manifold. So you can think of this as parameter of Calabi-Yau manifold. Well, in general, in physics, we take this scalar class to be complex value. So it includes actually NSNS B-form field also. But anyway, so you have these 2 sets of parameters. And for any parameters, you have 2-dimensional superconformal series. So that means that you can think of this as sort of a parameter of the 2-dimensional conformal field series. And you can deform 2 conformal field series by deforming scalar and complex moduli. Okay, so the way that we can do this deformation can be expressed in terms of these BPS operators. So for example, so to see that we can consider the following things. So suppose you take phi to be CC primary. And so it is annihilated by G minus 1/2 plus of annihilates this, and then G plus minus 1/2 bar annihilates this. So suppose phi is a CC primary, and moreover, let's assume that the left charge is 1 and the right charge is also 1. So then according to the formula I wrote over here, H bar is equal to 1/2 because it's a BPS state. So the H is 1/2 of absolute value of Q. So since I'm taking Q to be 1, so it should be like that. So suppose I take this such primary state and then consider multiplication of G minus 1/2 minus G bar minus of minus 1/2 phi to it. Okay, so let's consider this operator. It turns out that this operator is an exactly marginal operator. And so exactly marginal means that you can start from this Lagrangian for the Lagrangian density for the sigma model and deform it by adding, in general, there are several of such CC primary linear combinations of these operators. And then this still preserves, this system after deformation still preserves the conformal symmetry. So TA is now the moduli of conformal system. So if that happens, then this operator is called exactly marginal. Okay. So we can see that in the following ways. That first of all, it has a correct dimension for the marginal operator. Marginal operator in 2 dimensions must have the conformal dimension 1 for the left and 1 for the right. And this has the correct dimension by taking this into account. And since I have chosen this to have a charge 1 and 1 for the left and the right, and since these are supercharges have -1 charges, so the total operator is neutral. And it commutes. So if you integrate this to define the action, then this one, after integral, commute with all the supercharges. So let's see how this works. So for example, so let's consider this operator. So for example, if you commute with G minus 1/2, if you add G minus 1/2 to it, then since G minus times G minus vanishes, it's nilpotent. So it goes to 0. So that means that it commutes with G minus supercharges. Now, if you commute with G plus, then the commutator of this, anti-commutator of this, G minus 1/2 plus and G minus of minus 1/2 is actually the Virasoro generator L minus 1. This is a supersymmetry algebra. So that means that if you act G plus of minus 1/2 to this one, then this supercharge combined with this becomes L minus 1. And L minus 1 acting on the primary states is actually a derivative operator. So that means that this turns into derivative operator of G minus 1/2 bar minus acting on phi integrated over the 2-dimensional sheet. So if this 2-dimensional sheet is closed without boundary, then this integrates to 0. If you have a boundary condition, you just need to impose appropriate boundary condition. so that boundary contribution of this vanishes. So in any case, in that case, both of these are preserved. So that means that this is actually a nice exactly marginal perturbation. You can repeat this exercise for CC algebra, AC algebra. So that means that you have 4 types of exactly marginal deformation to this 2-dimensional conformal pixel. And these 4 correspond to the scalar deformation, and I erased this, complex deformation. And their complex conjugations. Okay, so I say that if you have CC, which is annihilated by this, then we can deform the Lagrange density by adding appropriate linear combination of this. And I assume that the Q and Q bar is 1 for these operators. So this actually corresponds in 1-to-1 to deformation of the Keras structure. Deformation. So in particular, the metric, the Keras metric, is deformed by adding some linear combination of K, which is an element of H11. So it's a cohomology with 1 complex direction and 1 anti-complex direction. And A goes from 1 to the dimension of H11. Okay, so in general, I use this notation that HPQ of the manifold is an element, is a PQ form. So namely that the differential form with the P holomorphic indices and the Q anti-holomorphic indices. Okay, and such that del of omega is 0, del bar of omega is 0, or rather, we can say that d of omega is 0, and omega cannot be written as d of something else. Okay, so this is a definition of the cohomology. And in particular, if you have a P holomorphic component and the Q anti-holomorphic component, we call that as HPQ. And if you use H11, you can deform the Keras metric, and that deformation is generated by the generator of CC, primary field. If you have CA, and that is annihilated by G plus minus 1/2 of phi is 0, and the G bar of minus 1/2 phi is 0. And I choose Q to be 1 and Q bar to be -1 in order for that to be compatible with this. Then we can also deform the Lagrangian by adding some linear combination of these fellows. In general, they run for different number of indices. Like that. And these correspond to deformation of the complex structure. By this I mean the following. So in general, we say that, well, what is the definition? What do we mean by complex structure? Complex structure means that the following things, that if we have a complex structure, then we know what kind of functions holomorphic on that manifold, right? Similarly, if you have differential manifold, we can tell what kind of functions are differentiable on that manifold. In the same way, we need to know when a function is holomorphic. So that means that in order to define complex structure, we need to be able to write the anti-holomorphic derivative operator. Because we can write down anti-holomorphic derivative operator, we say that the holomorphic function, so we say that function f is holomorphic if and only if it is annihilated by this holomorphic differential operator. So defining holomorphic differential operator is the same as defining the complex structure. But this holomorphic differential operator can be deformed infinitesimally in the following way, that if you have some kind of tensor on the manifold, which has one anti-holomorphic lower index and one holomorphic upper index, we can sort of mix holomorphic derivative with anti-holomorphic derivative, and therefore deforming the complex structure. In order for this deformation to be non-trivial, so that it cannot be absorbed into change of coordinate, then this eta should belong to some kind of cohomology. And in fact, if you lower the indices by holomorphic n form, I assume n is a complex dimension of this Calabi-Yau manifold, then it should belong to h n minus 1, 1. And if this belongs to this element, then you can actually generate a non-trivial complex structure deformation. And that is generated by this type of things. And you can actually show that there is one-to-one correspondence between solution to this equation and the element of this cohomology class. So you see that you can use this primary field to describe deformation of the sigma mod. Any questions? Okay. So there's actually nice way to restrict our attention to this BPS sector. So BPS sector is particularly nice because you can do lots of exact calculation. And then we can later interpret this exact calculation in terms of physical observables in string theory. And so one nice way, one powerful way to extract calculable quantity out of this BPS quantity is called a topological twist. So this is a sort of a basic ingredient when we talk about a large class of topological quantum field theory. So let me describe this. So in a simple term, the topological twist is the following operation. That suppose you have n equal to superconformal algebra. Generated by energy momentum tensor, which contains a Virasoro generator, and then pair of supercharges, and then the U1 current. These are all holomorphic quantities. These are all holomorphic fields in 2 dimensions. Then topological twist is the following operation. That is that if you have Lagrangian, then basically you deform this Lagrangian. Well, the action is an integral of Lagrangian density, but you deform the Lagrangian by adding some appropriate background field to this U1, background gauge field coupled to this U1 current. And this background gauge field is related to 1/2 of the spin connection on the world sheet. So you are deforming the two-dimensional sigma model by adding source to the current by introducing some U1 gauge field background coupled to the current, but in a controlled way. Since J is a conserved current, so we can calculate this effect of this deformation exactly. And one effect of this deformation is the following. So if you change Lagrangian, then you change the energy momentum tensor. So one way to deform the energy momentum tensor is to take functional derivatives of the action with respect to the metric on the world sheet. The spin connection depends on the metric. So if you add this term, then this term will give rise, this term depends on the metric on the worldsheet. So therefore, adding this term changes the definition of the energy momentum tensor. And if you follow this algebra, then you find that the energy momentum tensor is deformed by addition of a derivative of the U1 current. So introducing this background is same as deforming the energy momentum tensor by this addition. And if you deform the energy momentum tensor, then you change the conformal dimension of these operators. So for example, G plus used to be the spin 3/2 operator because it's a supercurrent. And it has left moving conformal dimension 3/2, right moving conformal dimension 0 because it's conserved. But after this deformation, it becomes dimension 1, 0. Just like the current J. It has the same dimension as an ordinary current. And G minus used to be the dimension 3/2, but now it becomes 2, 0 by this new energy momentum tensor. And they have the following property that each of them square to 0. They are each nilpotent operator, but if you take anti-commutation relation of the two, it becomes energy momentum tensor. So this is something familiar in string theory literature. If you have studied string theory 101, like introductory chapter of Polchinski's textbook, for example, you see that the way that to describe the string theory worldsheet is that you have BRST operator and you have ghost and anti-ghost corresponding to the diffeomorphism invariance of the worldsheet. And so that the commutator of BRST operator and anti-ghost give rise to energy momentum tensor. So you see that the G plus and G minus would behave just like BRST operator and anti-ghost. So more specifically, since now G plus is now dimension 1 operator, we can integrate this over any one-dimensional cycle over worldsheet. And then you can define some operator, which I'm going to call BRST operator. And by definition, by construction, this BRST operator is nilpotent. So we can consider cohomology with respect to this BRST operator. And then if you compute anti-commutator of this BRST operator with G minus, then this becomes, it becomes this modified energy momentum tensor, the twisted energy momentum tensor. So that means that it is just as if it is an ordinary bosonic string that you have BRST operator and you have anti-ghost. So we learn in the introductory chapter of Polchinski's textbook, for example, how to define string theory amplitude. So for example, if you have genus G Riemann surface, we consider moduli space. So this is a genus G surface. Then we can consider moduli space of this genus G surface, which we call MG. And we can consider integrating appropriate insertion of G minus operator. And we can also do, and we need 3G minus 3 of them. And we also introduced the same number of operators for the right mover. One of the things about this moduli space is that its dimension is 6G minus 6. So if you insert 3G minus 3 of this and 3G minus 3 of this, then it gives you actually the top form on the moduli space of Riemann surface. So you can integrate this over moduli space of Riemann surface. So if you can calculate this, then it gives you a G-loop action function for this string theory. Okay, so this is what is called the topological string at amplitude. So far we have been considering conformal field theory on a fixed two-dimensional Riemann surface. But if you topologically twist it, then we can consider integrating this amplitude over moduli space of Riemann surface. Okay. So if we can do this, then it's nice because we can, and then there are a variety of other observables that you can define for this topological string set. There is one, however, catch, one important subtlety that we need to I need to mention, which is the following. So in general, because you have this U1 current for left mover and the right mover, so in general you have to make sure that whatever you calculate is consistent with conservation of U1 symmetry. Okay, so G minus has carried charge; it carries -1 unit of U1 current. So if you insert this 3G minus 3 of them, then this operator has negative charge. So in order for this quantity to be non-zero, it has to be cancelled by something else. So it turns out that it's actually nicely cancelled by the presence of this background gauge field. But in order for this cancellation to work, the target space Calabi-Yau manifold has to be of particular dimension. So it turns out that if the complex dimension of the Calabi-Yau manifold is 3, then this is non-zero. That is that you can insert exactly 3G minus 3 of this G minus current to get the non-zero amplitude. That in general, the amount of extra U1 charge in the background generated by the spin connection term is proportional to the dimension of the target space. And if this is three-dimensional, the complex three-dimensional, that is real six-dimensional, that is the case that we talked about yesterday, then this quantity is not there. So it is exactly in that case that you can calculate this. So this is nice. And in other cases, you need to insert other additional operator in order to make this non-zero. Okay, and we can also do that in certain cases. But complex Calabi-Yau 3-4, real six-dimensional Calabi-Yau manifold, the complex three-dimensional Calabi-Yau manifold, is a particularly nice thing because we can define it without any additional structure. Okay. Oh, I shouldn't have erased this, but I'm erasing it. So let me just erase the whole thing. So I defined the topological twist here, but in fact, I have only defined the topological twist for the left mover, and I could have also defined topological twist for the right mover. And also, there's another thing, which is that here I have chosen the twist in such a way that G plus becomes dimension 1 and G minus becomes dimension 2. But for example, I could have chosen another twist. For example, if I had chosen minus sign here, then I would have gotten minus here. So in that case, instead of this, this becomes 2. and this becomes 1. So in that case, the role of plus and minus will be exchanged. So if you have chosen opposite sign here, then G minus becomes the BRC operator, and G plus becomes the antigot. So in fact, there are 4 different choices of topological twist, but 2 of them are complex conjugation of the other 2. So essentially, there are 2 non-trivial different, 2 physically different choice of topological twist, and they are called A model twist and B model twist. So A model twist is a one of which BRC operator is given by integral of G plus for the left mover and G bar minus for the right mover. And B models are the one where BRC operator is given by G plus and G bar minus. So for A model, it's G plus and G plus. Okay, so in this case, if you make this choice, then you see that the CC primaries are physical. Physical in the sense that it is in the non-trivial BRC cohomologies. And all other primaries are trivial in a sense that if you consider CA primaries or AC primaries or AA primaries in the context of A model, they are all trivial in the BRC cohomologies. So only CC primaries are physical in this case. And CC primary correspond to the deformation of Kähler structure. Okay. Similarly, if you consider B model, then CA primaries are physical. So that corresponds to deformation of complex structure. And so this topological twist is a very nice way to extract either deformation of Kähler structure or complex structure out of these possible 4 different types of deformations. And another nice thing is that because of this, any observables that you can calculate in the context of A model, such as this FG. So for example, FG and other observables in the A model depends only on Kähler structure. And not on complex structure. And similarly, if in the A model, it depends only on Kähler structure. And similarly, if you consider FG and other observable in the B model, then they depend only on the complex structure. Okay. So this is sort of this helps us enormously because, for example, if you are interested in calculating B model quantity, then we know a priori that whatever you calculate in B model depends only on the complex moduli, so it's independent of Kähler structure. So in particular, you can take the size of the Calabi-Yau as large as you like. Because the size of the Calabi-Yau, the volume of a Calabi-Yau is parameterized by Kähler structure. But if you take if you take some fixed Calabi-Yau space and take the volume uniformly large, what's going to happen is that curvature becomes smaller and smaller, right? But in the case of sigma model, the curvature is the one that controls the strength of the interaction. Remember that the Lagrangian density has this form that you have a metric in the target space, and then it depends on target space coordinate, and then you have this kind of Lagrangian, and then there are fermions like that. So the reason that this two-dimensional sigma model is a non-trivial quantum field theory, that's an interacting quantum field theory, is that it depends on, there is an X dependence here. Okay, but this X dependence is the same as having curvature, because curvature tensor is related to two derivatives of the G. So X dependence of G is related to the curvature of the target space. But if you take the size of the Calabi-Yau larger and larger, the curvature becomes smaller and smaller at each point. So that means that the interaction becomes weaker and weaker. Okay, so that means that in fact any quantity in B model you can calculate exactly by just doing semi-classical calculation of the two-dimensional sigma. You don't have to worry about loop corrections, for example, in order to calculate B model quantity.
So basically, I have, so in these B models, the deep IR physics are better understood. Like it is freer of singularities. Can I put it that way?
Yeah. So you can reduce any question about the B model to question about classical mathematics that the mathematician had to figure out how to calculate, at least for small number of G's. That for higher G's, there are some non-trivial things. But for the simpler cases, and most of the calculation in B model is related to some classic mathematics. Okay. A model is more interesting because it has some quantum mechanical effect, because now it depends on Kähler structure. And I will try to exhibit it if I have time. I only have 45 minutes more.
Okay, thanks.
Okay. Okay, so let me give you one example where you can actually do the classic mathematics of Calabi-Yau manifold, or more general this type of complex manifold, inform us about the structure of some physical observer. So one of the important observable in this kind of quantum field theory you can calculate is the Thermological Method. It is a metric in the space of exactly marginal deformations. Okay, so this is a metric in the space of deformation. So I told you that if you have Lagrangian, then you can deform this Lagrangian by adding some operator G and G bar, acting on some CC ring, CC primary or CA primaries, etc. And so this is the exactly marginal operator. Okay, so but since there's a state operator correspondence in quantum field theory, so there's a corresponding state, and if you have a state, you can compute inner product of between these two different states, and it gives you a metric in the space of exactly marginal deformation, and that is called the Thermological metric. So the Thermological metric is a very important concept. It gives you the metric on the moduli space of conformal field theory. So this shows up in variety of important calculations in conformal field theory. But so since this Thermological metric can be defined in a topologically twisted theory, because if you are interested in calculating Thermological metric for Kähler structure, you can just go to A model and calculate it. if you are interested in calculating the thermological metric for complex deformation, complex structure deformation, you can go to B model. So that means that you can actually define the thermological metric in the context of topologically twisted theory. And so therefore, so that in particular means that if you are interested in the thermological metric of the B model is independent of scalar structure. So that means that you can go to large volume limit, and then you can just do the calculation in semi-classical approximation to quantum field theory. And so that's just reduced to the classical mathematical program. So we can use a known result of the complex deformation of manifold that the mathematician had figured out, and use that to calculate the thermological method. So let me use maybe 10 minutes or so, maybe 5 minutes, reviewing how a mathematician would calculate such thermological metric or metric in the space of complex deformation, and then try to interpret this in the physics language. Okay, so here's how a mathematician would calculate the metric. For simplicity, let's consider the case of complex dimension of Calabi-Yau to be 3. So the Calabi-Yau threefold. We can do it in any dimension, but just for the notational simplicity. So in this case, we consider holomorphic threefold. So you remember that this played an important role in the study of Calabi-Yau condition, because the rich curvature of the scalar manifold is proportional to del del bar of log of determinant of the metric. So therefore, the determinant of the metric of Calabi-Yau turned out to be related to the product of holomorphic threeform and its conjugation. So then it's natural to calculate the norm of this holomorphic threeform as an integral of omega with omega bar integrated over Calabi-Yau manifold. Since this is related to the determinant of G, you can also think of this as a volume of the Calabi-Yau manifold. It turns out that this actually gives you the scalar potential for the moduli space of Calabi-Yau manifold. So if I call the MC as a moduli space of complex structure of Calabi-Yau manifold, then, so suppose dimension of the moduli space, the complex dimension of the moduli space is the same dimension of Hn minus 1. So let's parameterize this in terms of a set of coordinates Ta, where A goes from 1 to Hn minus 1. Okay. So then it turns out that the metric, the thermological metric, TAB bar on MC is itself a scalar metric. So Calabi-Yau manifold, the target space of the sigma model is a scalar manifold, but the thermological metric of its moduli space is also scalar. So being scalar, the metric can be written as del A, del B bar of K. And this scalar potential is related to this omega. It turns out that this is given by exponential of K minus K. Okay. This can be actually seen in the following way. That essentially what happens is that if I take derivative of this holomorphic threeform with respect to the complex deformation, if you deform the complex structure, so essentially it gives rise to this eta A that I talked about previously, namely that you have one you see that so eta had one complex coordinate, complex indice and one anti-holomorphic indices, which sort of get mixed with omega by if you take one derivative. So that means that if you take one derivative with respect to holomorphic coordinate, you get the distance into eta, and if you do it once more, you get eta. So you can show that if I take del A, del B bar of K defined in this way, then it is related to 1 over omega times integral of eta A with eta B bar integrated over the Calabi-Yau manifold. And this is exactly the classical expression for the metric in the space of complex deformation. So you can actually calculate this metric very explicitly. And in fact, there is a mathematically well-defined procedure of how to calculate this thing using relatively simple thing like a hypergeometric differential equation. So let me just briefly tell you how this works out. So you see that what it boils down to is in order to calculate a metric in the moduli space, what you need to do is to calculate this quantity over Calabi-Yau manifold. Okay, and so there is actually a nice method of calculating this quantity. It's called Riemann bilinear identity. So let me explain the following. Let me explain this. So the Calabi-Yau manifold is complex three-dimensional, so the real six-dimensional. So let's take some middle dimensional homology of this manifold. Okay, so you have a basis for this middle dimensional homology. I goes from 1 to H12, 0 to H12. Okay, and then the Riemann bilinear identity essentially says that this is equal to sum over this basis of integral of omega alpha I and integral of omega beta I minus its conjugation. So if you can calculate the period of these holomorphic differentials, then you can calculate the scalar potential for the modular space. And so let's denote xi to be an integral result of this integral of alpha I. And then let's calculate this as an integral of this. Okay, so let's define this in this way. So then there's a famous theorem in algebraic geometry called Twilight theorem, which is valid in this case, which is to say that xi determines complex structure. It is very similar to what happens in the case of a two-dimensional surface that you might be familiar with. For example, if you have a torus, right? So how do you parameterize the complex structure of the torus? Well, you have this period tau, right? And what you do is that you normalize this to be 1, and you call this tau. But it's just like a ratio of the two periods. Right? So therefore, the length of this period specifies the complex structure. So it's similar here. So if you calculate, if you know this xi determines the complex structure, so that means that in particular fi must be a function of x. Okay, and but there is some redundancy in this parameterization, because if you have the omega is a holomorphic 3 form, then you can calculate x, but you can multiply any complex number, non-zero complex number to omega, and this is also a good parameterization, a good way to define holomorphic 2 form. So in fact, the overall scale of x does not give you the complex structure moduli. So in practice, what you have to do is to choose appropriate direction, say 0, and then take the ratio of this, and then use this as a coordinate in the complex moduli space. So this is called the flat coordinate. And if you have flat coordinate, then you can calculate this. You can specify the complex structure. If you rescale x, f is also rescaled. So that means that this is actually a homogeneous function. So if you multiply constant, you get some constant like that. So that means that if you scale out the c, f is also essentially the function of t. Okay. And the nice thing about this is that this quantity, this dependence of this f on x, can be calculated using partial differential type equation of the type of hypergeometric differential equation. So many of this kind of period integral reduces to the program of solving hypergeometric type differential equations. So when you look at the literature of mirror symmetry and Calabi-Yau, you sometimes encounter hypergeometric differential equations. And the reason that happens is that people are calculating this type of period integral of holomorphic forms. So if you solve the hypergeometric differential equation and determine f as a function of x, then essentially everything you need to know about the moduli space of Calabi-Yau space gets known. And then K is determined, the scalar potential is determined in this way by minus of log of xi fi bar minus xi bar fi. So everything can be found explicitly. And but this is a classic B model case. But whatever you can say about B model happens in A model too. So in this type of structure is also hidden in the A model. And you can actually derive all these structures like flat coordinate and period integral, etc., for the A model too. And in fact, more generally, if you have n equal to superconformal field theory, then the space of deformation, marginal deformation of this two-dimensional sigma model are described in this kind of structure. So these structures are called TT star equations. TT star summarized in the TT star equation. So this was developed by Cecotti and Buffer in the early 1990s. And this essentially follows from the word identities of n equal to superconformal symmetry. So here, I derived this type of structure by using mathematics of the Calabi-Yau manifold. But in fact, this follows from all these things follows from word identity of the superconformal symmetry. Okay. So I have half an hour left, and So I'd like to make maybe one interesting observation about some calculation that one can do using this technique. And this is a model of ADS CFT correspondence. So let me end with that. So this type of calculation using topological field theory have been developed over the last 30 years, and there are lots of interesting results now. But let me give you one interesting facet of this kind of result, which is a toy model of large N duality. So of course, if you talk about large N duality, ADS CFT correspondence is the most important and famous example. And but it is a sort of difficult example because you don't have access to a situation where you can do both string theory calculation and gauge theory calculation, right? In some regime, you can do gauge theory calculation nicely by using perturbative regime, but that corresponds to strongly coupled gravity situation in the uncertain space. And conversely, in the case when you can do weakly coupled gravity description, you find that the conformal field theory is strongly coupled. So there is no single regime where you can actually do controlled calculation in a simple manner. In some cases you can do, but in a simple manner in both cases. And of course that's good too, because then you can use ADS CFT correspondence to sort of teach both sides gravity and conformal field theory, but it does not help us understand the mechanism of large N duality in detail. But in the context of topological string, actually you have an example where you can actually calculate both sides exactly in in any regime. But I have to first tell you what I mean by large N duality in the context of topological string. And in the context of topological string, large N duality means the following concept. So I define f of g as an integral of genus G string amplitude integrated over moduli space of genus G circles, right? And so you calculate G loop amplitude, G loop string amplitude, and integrate that over moduli space and define Fg. But large N duality relates closed string, which contains gravity, to open string, which contains gauge theory. Large N duality is also a duality between closed string and open string. So in order to formulate large N duality, we should consider generalization of this quantity, where you can have several boundaries. So in addition to the handles, you should consider adding boundaries. But in general, there can be different types of boundaries. So you can parameterize boundaries by some indices. So you can call this boundary 1, and you can call this boundary 2, etc. So you can ask, well, how many boundaries of type 1 exist? So we call this N1, N2, etc. So suppose we have N1 of this first type of boundary and N2 of the second boundary, etc. So let's define this amplitude in this way. So suppose there are k types of different boundary conditions, and suppose you have genus G Riemann surface with N1 of first type of boundary, N2 of the second type of boundary, nk of the case type of boundary, for example. So suppose you have such open string amplitude. So if FFG is a genus G amplitude with the total of n boundaries, which is n1 plus n2 plus all the way to nk. Okay, so suppose let's consider this kind of amplitude. So the Largian duality, what I mean by Largian duality is a relation between this kind of things and this kind of things. And I would like to give you an example of this. So how can you relate this kind of things and that kind of things? Well, in order to see that, we need to. I would like to remind you how the 't-Hooft or the original idea worked. In the original idea of 't-Hooft was that you consider gauge theory, and if you have a gauge field, he wrote the gauge field as double line because it's in adjoint representation, and the Feynman diagram of gauge field was something like that. So you have lots of holes in the amplitude, right? And each hole was weighted by 't-Hooft coupling. And then what he suggested do was to keep the 't-Hooft coupling finite. So let's call T as 't-Hooft coupling. And then consider some particular topology given by this 't-Hooft this type of diagram. Okay, so you can think of each of these loops as a hole on the worldsheet. So each hole is weighted by this 't-Hooft coupling. And you sum over this amplitude with this fixed 't-Hooft coupling. And then the idea is that this is related to the closed string. So we can generalize this idea in this case. So for example, suppose you have a topological string amplitude with variety of different boundaries. What we can do is to introduce analog of 't-Hooft coupling for each type of boundary and sum over them. So what you do is to sum over the all possible number of boundaries. So I have T1, N1, T2, N2, Tk, Nk. And in general, yeah, so let's consider this kind of things. So then you get some amplitude which depends on G and which depends on these parameters. So if you can understand, if you can interpret this generating function, you may call, of the number of boundaries as some kind of closed string amplitude, with T1 to Tk as a moduli of closed string, where originally these are just the boundary counting parameter, but if you can interpret this boundary counting parameter as a moduli of closed string theory, then we can say that there is a open closed string duality, because this is an open string amplitude, and this is a closed string amplitude. So we have been, so if we can establish something like that, then we can say that there is an example of 't-Hooft duality, that Largian duality relating open string amplitude to closed string amplitude. So I'd like to present an example of such correspondence. Okay, so I need to give you an example of open topological string theory where I can do this summation of Tohuft coupling and relate that to closed string amplitude. Okay, so I'd like to end that with that example. Okay, so first I need to I need to tell you what kind of open string we are going to consider. So this is actually an example which was actually considered by Ed Witten in the early 90s. And so this was a following kind of model. So you consider a model. And you need to consider it on Calabi-Yau manifold. But here I'm going to consider a non-compact Calabi-Yau manifold. And in fact, I'm going to use cotangent space of 3 sphere as a target space. So in fact, this is an example of non-compact Calabi-Yau manifold. 3 sphere has a positive curvature. But if you consider cotangent space, the cotangent direction has opposite curvature, so that the total rich curvature for the 6-dimensional space, you have 3-dimensional base and 3-dimensional fiber, and the total rich curvature is actually 0. And you can introduce a nice scalar structure to it. So it becomes a non-compact Calabi-Yau. So we have to have an open string theory of it. So in order to have an open string, we need to have D-branes. So what you do is wrap n D3 brane on S3. So then what you get is that you get the UN gauge theory on S3. And what we can show was that this UN gauge theory is nothing but the Chern-Simons gauge theory. Namely, the integral of 1/2 of A dA plus 1/3 of A cubed with gauge group SUs UN, and then you take trace, and then you integrate, and then there is a level of the Chern-Simons theory. 4 pi, the k over 4 pi. Okay, so you have 2 parameters n and k. So k is like 1 over coupling. So in fact, the coupling constant of this theory is lambda, which is given by 2 pi I over k plus n. And then the Hooft coupling is n times lambda, which is given by 2 pi I over n and k plus n. So this is a Hooft coupling. Okay. And since Chern-Simons theory is an exactly solvable theory, so we can calculate the partition function exactly. So there is a closed formula. So we have e to the I 8 pi n minus 1 divided by k plus n to n over 2 square root of k plus n divided by n, and product of s equal 1 n minus 1 2 sine s pi over k plus n raised to the n minus s. So this is actually the exact formula for the partition function of this Chern-Simons theory on S3 to all order in coupling constant and the Hooft coupling. Okay, but if you rewrite this quantity in terms of lambda and t, then this is all order result in this type of coupling constant. And because of this connection between Chern-Simons theory and topological string on D-brane wrapping on S3 of Calabi-Yau, we can relate it to the open string amplitude in this way. We can calculate fg of n, lambda 2g minus 2, and t to the n. So in particular, for fixed order, for fixed power in lambda, we can do that calculation exactly. So since we know the exact expression for the open string partial function, so we can do this calculation in that case, and we can see what kind of result you get. So let's call this as z of t and lambda. It depends. This one is expressed in terms of k and n, but we can use this formula to rewrite it in terms of lambda and n, lambda and t. So we can write f, t, and lambda as exponential of minus sum over g, lambda 2g minus 2 of fg of t, where fg of t is sum over n of fg n t to the n. Okay, so we can calculate this using that formula. So it turns out that so this is what we wanted to do. So the question is that this is open string amplitude. Can we interpret this as closed string amplitude? So it turns out that this has actually a very nice expression. You can actually expand. You can resum this series. You can resum this series and write this in the following way: that it is actually constant minus 1 to the g minus 1, 2g minus 3 factorial times 2g minus 2, and Bernoulli number times summation m equal 1 to infinity of m 2g minus 3 of e to the minus mt. So, and each one of them turned out to have a nice interpretation in terms of closed string. So for example, this combination, so Bg is a Bernoulli number. And then this combination, or including this minus sign, is actually the Euler characteristic of the moduli space of closed Riemann surface of genus G. And this constant piece is also a Chern class calculation of a moduli space of Riemann surface, where Cg minus 1 is a Chern class of what is called Hodge bundle over this moduli space. So both of them have a nice closed string interpretation. And moreover, the entire thing has an interpretation as calculating closed topological A model on what is called resolved conifold geometry. So, Fg of T turned out to be an A model closed string on the resolved conifold. So let me explain this a little bit. So to resolve the conifold is the following geometry. So resolve the conifold. So first of all, I have to define what we mean by conifold. So conifold is a solution to this equation. In C4. So we have one complex equation in 4 complex dimensional space. So this gives you 3 complex dimensional space. And it turns out that this gives you a Calabi-Yau manifold. And it's called the conifold. But this conifold is singular. That is singular at the origin. When x, y, z, w are both 0, then this equation degenerates. So there is a singularity at the origin. So there are so it is often denoted by some kind of cone. Where here is a singularity over here. This is some kind of caricature of conifold. And the apex of this conifold is singular because 2 kinds of cycle vanishes. So there is a 3-dimensional space, 3-dimensional sphere, and 2-dimensional sphere, and both shrink to a point at this pinnacle, and that makes this space singular. So there are actually 2 different ways to make this space smooth. One is to make the size of S2 finite at this pinnacle, and the other is the size of this S3 finite at this pinnacle. So there are 2 different ways of making this space smooth. So yes.
Small question. So when you write x square plus y square plus z square plus w square, this is x mod, as in mod x square, or just like you take a complex number and just square it?
It's a complex number square.
Okay. Oh.
Yeah. So I said it's in solution equation is C4, and this is x, y, z, w.
Okay.
X, y, z, w is the coordinate of C4.
Oh, okay.
Okay. So there are 2 ways of making this space smooth. So one is to make the S3 finite. Okay. It turns out that the resulting space is actually nothing but the cotangent space of S3. Because what's the cotangent space of S3? Well, you have a base, which is S3, which has a finite radius. And at each point, we have a tangent space. The tangent space at each point is almost like, it's like R3, right? So R3, if you have R3, then you can consider S2 encircling the origin of S3, R3, and this S2 shrink to a point. Right? So you see that therefore the structure of the cotangent space looks exactly like this caricature, where as you go to the base, as you go to the origin of this cotangent space, then you have this base S3, which is of the finite size, but S2 shrink to a point. So this is actually the base of cotangent direction of cotangent space of S3, right? And what we are doing here, what Witten was doing here, is to wrap ND3 brane on the base. So here you have ND3 brane. That's what Witten did over here, right? So, but so this is open string theory, because open string can end on this D brane. So there are open string ending on this like that. So these are open strings. Okay. But what happens is that there is another way of resolving it, which is to make S2 large. So instead of making S3 large, we might consider S2 large. So as you go to the pinnacle, S2 does not shrink to the zero size, but have finite size, and it turns out that that size is parameterized by that T, the two-first factor. Okay? And so here you have open string on this geometry, and here you have closed string on this geometry, and then this equality. The Chern-Simons partition function can be expressed in terms of closed string amplitude. Means that these are the same. There is an equivalence between them. So what happens is that you start with this kind of deformed conifold geometry where S3 does not shrink, S2 shrinks, and wrap D-brane on it, and somehow existence of D-brane changes the geometry so that you go to this resolved conifold situation. Okay, so this is a nice toy example of large N duality where we can see microscopically how the open string calculation reduces to closed string calculation. And in some sense, this is very much like in the spirit of ADS-CFT correspondence. So let me end this by telling you how this is very close to ADS-CFT correspondence. So remember it, how does the ADS-CFT correspondence works? In the typical example, you have N D3 brane in 10-dimensional Minkowski space, right? So let's draw the, let's consider a 10-dimensional space. So we have a 10-dimensional space, and then let's write the, so you have D3 brane, so it spans out 4-dimensional direction. So let's draw this 4-dimensional direction to the vertical direction. The vertical direction is R4. And there is a remaining 6-dimensional direction here. So you have ND3 brane over here, right? You have ND3 brane at origin of R6, which is a direction transverse to the D brane. And D brane is extended in 4-dimensional direction. So in this case, you see that there is a S5 surrounding S3, and this S5 shrinks to a point around D brane. Okay? But on the other hand, we say that this is equivalent to ADS5 plus S5, where this S5 corresponds to this S5. But this S5 does not shrink anymore. This S5 does not shrink anymore. Instead, what shrinks is the boundary of ADS5. So suppose, for example, instead, let's consider Euclidean case. If you consider Euclidean case, you have S4 here. And you have a Euclidean ADS. Euclidean ADS is like a disk with boundary S4. So in the case of ADS-CFT correspondence, in the ADS side, this S4 shrinks. To a point. Right? Then this S5 does not shrink to a point. Whereas in the gauge theory side, this S5 shrinks. And this S4 does not shrink. So the rule of S5 and S4 is exchanged in the open string side and the closed string side. Somehow, by wrapping n d-branes on this S4, forces this S4 to shrink to a point and somehow inflate S5 to stay at the finite size. That's how the ADS-CFT correspondence works. And this is exactly the same thing that is happening in this situation too. In this case, S3 shrink to a point, the S2 shrink to a point, but somehow putting d-brane on S3 make it shrink, and instead the dual side opens up. So this is sort of a nice toy example of how ADS-CFT correspondence works. It would be very nice to make this correspondence more precise. And in fact, several years ago, Kumran Bamp and I, and also partially with Nathan Berkovich, tried to make this analogy more precise. And we have only made some partial success in that. But I think it would be very interesting to understand this more. So anyway, so I think I have exhausted my 3 hours, so I should stop here. I wish I have more time that maybe next time when I go visit Korea, maybe I can have some sequel of this lecture. But for today, that's my lecture. Thank you for your attention. I'd be happy to take any questions.
Thank you very much, Hiroshi. So that was a wonderful set of lectures. I really wish we had more time to enjoy the sequel of your lectures. By the way, so before we go to Q&A session, I have an announcement. So we'll have a group photo session after the Q&A. So please remain seated. Okay, so let's have Q&A. So if there's any questions from the audience, then please. If not, I do have some vague questions.
There is something on the comment section. Is that
Oh, the comment was about, yeah. Thanks for the masterly crystal clear.
Okay. So that was not okay.
Okay, so just let me start my own question. So, so you already mentioned that there's a kind of way to derive this duality. I have this vague question that, in recent years, there's people have been trying to use this idea of like quantum entanglement and use that to show that emergence of bulk geometry from the field theory side. Can you maybe make a comment on that in view of?
So that's a very interesting question. So in my talk at the Korean Physical Society meeting last week, I gave a talk about more recent work where we used the entanglement wedge reconstruction of the holography in the ADS-CFT correspondence to make statement about the gravity in ADS. And so there it was very important that the local information in gravity side in ADS are encoded in entanglement of the boundary state. Okay, so somehow in the case of ADS-CFT correspondence, the entanglement plays very important role, and in some sense, the holographic map is a quantum error correcting code. That seems to be the message that we are learning over the last few years in the recent development in holography. That's one of the very important things. And that is sort of, for example, in the recent development in the page curve and the island formula, that's also featured. And so then you might wonder whether this is somehow featured in any of this discussion. That's a very interesting question. So for example, in this particular case, the analog of boundary theory is a Chern-Simons theory. And in Chern-Simons theory, you don't have local observables. You do have some extended observable like knot and links. So for example, observables in ADS and in the CFT side. So in the case of Chern-Simons theory, like Wilson lines going around like that. So these are the observables. And then there is actually a corresponding quantity on the dual side. So I need to think. This is a very interesting. I have not thought about that, but this is a very interesting question. Whether there is any way to sort of characterize the entanglement structure in the Chern-Simons theory, and then see whether this is reflected on the gravity side. One of the things is that so for example, both sides are topological. So somehow the notion of entanglement between different points is a little bit vague, because somehow this at least at the spatial level, it seems to take into account some local information. So locality seems to be important, and somehow in the topological field theory setup, that information is lost. But
right.
But maybe there is something to it. I have not thought about. This is a very interesting suggestion. Maybe this is a project on its own. But I'd be very happy to think more about this. That sounds like a very good suggestion to me. Yeah, thank you.
Right, thank you. Okay. Any questions from the audience? Okay, I guess the lecture was really crystal clear.
Thank you.
So, okay, so let's now have a group photo session. So
okay.
Everyone, please turn on the video.
Nice to see everyone now.
Okay. Right, there's still someone. Okay, yes. I see there's some people who doesn't have a video, but okay.
Well, I don't want to force people to turn on their videos.
Yes, so I'm gonna take a quick screenshot. So please look at the camera and I'll count on 3. 1, 2, 3. Okay, and I take another one.
Okay.
1, 2, 3. Thank you.
Thank you.
Thank you.